We have another one, this one, and I translated the title of the message: brightest exoplanet ever discovered, and it has titanium rings. This planet should not exist. Well, it does. So explain that, right? The thing is, look at the numbers again. So we look at the mass, well, roughly the sun's mass, slightly smaller, slightly less luminosity, probably because it's younger than the sun, and the luminosity of the sun will change too when it grows older. But roughly sun-like star, and we did transit observations with TESS. TESS is also a satellite that did these measurements. We find a radius that's slightly bigger than Neptune, with a mass, well, more than Neptune, so a density roughly the same as Neptune. So what is the case? Well, 19 hours, we have a winner. 19 hours around its star, so really fast. And with a sun-like star, it doesn't matter, it's still very hot. This is the equilibrium temperature, but also the front side is even hotter, 2000 degrees. And we call this one of the planets in the Neptunian desert. It's not an actual desert, but if you make a diagram with masses and sizes of planets, then basically there's an area where we don't expect many planets to be, because basically the size is too big for their mass and their gravity to contain all that atmosphere. So we expect planets to be in certain parts of this diagram, but not everywhere. But this is a planet that's actually in that roughly empty space. It's a special planet. The thing is, the Cheops satellite, the characterizing exoplanet satellite, it's a bit forced, this abbreviation, but okay. They wanted a nice abbreviation, and then they thought of the name afterwards. It really does. It sometimes happens like that. But they found this albedo of 80%. And basically what they did, they actually measured this infrared radiation from the planet by measuring the total and then subtracting the star, right? And then you can find the actual temperature. And they found such a high temperature that means that they have a very high albedo here, 80%. That's really reflective. It's more reflective than that wall, right? We have reflective surfaces like white walls and stuff like that, and in the paint usually it contains titanium oxides. So we scientists expect that the planet has clouds with titanium oxide. So to do stuff like this, right? And if you have clouds are condensations. Basically, clouds are small liquid spheres just floating in the air. They condensate, and sometimes they fall down. So yeah, you can have titanium rains, or titanium rains. Titanic rains is a lot of rain. Titanium rain, right? Yeah.
Do they have seawater as well?
I don't know. I no idea.
They only measure the titanium.
Well, no, the titanium is from a model to explain this albedo, right? So we have to explain why this planet is so bright, because it's very bright. They found that. And then basically means the clouds are so white, and we have other measurements that we expect the clouds to have titanium oxides, right? So, but I wouldn't know what's on the surface, but we can measure stuff from the atmospheres. If light of the star goes through the atmosphere of a planet, and we measure that, and then we measure the light of the star without the planet, and we take the difference, then we find the effect of the atmosphere of the planet on the light. And that tells us something about the chemical composition of the atmosphere. Yeah? All right. So it might look like this, an ultra-hot Neptune, right? I don't know if it's bluish, but Neptune is bluish. So, and it's nice to look at. So it's again, it's an official picture of NASA, but of course there's a guy who earns a lot of money making these illustrations. So, but it's nice. I mean, nice to look at. And might look something like this. So there's another one, K2-18b, nice name, but K2 is basically the second batch of observations that Kepler did. So Kepler's second light, as we say. And then the 18th star it observed, and the first planet it discovered. So let's look at the numbers again. So the mass is roughly half the sun, the radius roughly half the sun. The luminosity, well, this is, what is this, 2.5% or something, much less. It's a red dwarf, right? So we have many red dwarfs in the galaxy. And let's look at the numbers. So we have a planet that's smaller than Neptune, bigger than the Earth, all right? So it's somewhere in between. Mass, somewhere in between. And then we can calculate the density, roughly half Earth. So we expect it to be perhaps slightly rocky, but also with a hydrogen envelope, because we have to get the density down. So if it's all rocky, like the Earth, you expect high density. But if it's all ices and gases, you expect very low density. So this is just a guess. So a rocky planet with a hydrogen-rich envelope, just to explain these numbers, right? It is going about a star in 33 days, which is short, but it's a tiny star, right? So not too bad. This distance is small. Look at this. Equilibrium temperature, -8 degrees. Not bad. This is the equilibrium, right? This is sort of average. So there might be places that's above 0. And with normal air pressure, that means liquid water, if you have water. But basically water is everywhere in the universe, so that's not a special thing. So water vapor, it has to be, I mean, you have to really see it, and it has been seen. Also, well, we expect an ocean underneath high pressure ice, but the James Webb Space Telescope has discovered methane and carbon dioxide. Again, not very special, but nice that it's there. But this is special, dimethyl sulfide. So are there biologists here? No? No, okay. Dimethyl sulfide is special because on Earth, practically all the dimethyl sulfide is produced by phytoplankton, by organisms. So, I mean, that doesn't mean there are organisms there. Perhaps there's a geological or a chemical reaction that produces dimethyl sulfide, but still, it's intriguing, isn't it? There might be something like phytoplankton. I'm not assuming really two-legged aliens walking around, but I mean, simple algae or phytoplankton, small stuff. I'm expecting small stuff to be more present in the universe than actually aliens with arms and legs. But still, this is intriguing. So that's something. So we found this planet, and I don't know what the distance is to this planet, but basically this is all in our Milky Way, right? So this is very close. And then it might look something like this. So you see this sort of ocean-like planet with some clouds, of course. If you have liquid on the surface, then you probably have clouds, right? And then the reddish star. If you look at the previous picture, by the way, see what they did? This is the official picture. So they didn't agree with the color. They basically changed the color. Well, let's make it more red, all right? All right, more red. So okay, not. It's a bit dodgy, but okay. This is the official picture, okay, or official illustration, I should say. So we had another one, this one, Wolf 1069b, and it was discovered with radial velocity observation, so that's nice, by a Spanish instrument, and this is really forced. Come on, Carmenes. Is there a Spanish? Yeah, you speak Spanish. Carmenes. Sounds nice, but come on. Calar Alto high resolution search for M dwarfs with exo-Earths with near infrared optical shelter. That is force, isn't it? I mean, you start with Carmenes and then you go, oh my God, I have to think of the wording, but okay. But fair enough, it did these observations, so that's nice. So we find the star much less massive than the sun, smaller than the sun, even less luminosity than the sun. It's also a red dwarf. So we found this planet, slightly heavier than the Earth. Perhaps this is a guess, slightly bigger than the Earth. It's not a strange guess, but okay, we expect the same density. So roughly this composition, a third iron, two-thirds silicates. So probably a rocky planet, assuming this. So a short period, but as you know, with these red dwarfs, that's not a problem. So we think it receives less energy from its star, but possibly there's liquid water present. So if we make a temperature map of this planet, it looks like this, because of the closeness. Probably this is also locked with its front side, watching the star, basically, tidally locked. So its front side is always in the sun, and this red circle is the circle where the temperature is 0 degrees centigrade, Celsius. So within the circle, we have liquid water, perhaps, and outside it's probably ice, but this is intriguing. So we have this ocean in front of the star, right? And it has liquid water, probably. So if you have a stable situation with stable sunlight, with chemicals, with liquid water, stuff can happen, right? chemical reactions, perhaps even the complex molecules that we need for life. So perhaps it looks like this. This is very nice, of course. People love this stuff like this. Of course, also an illustration. So we have this red dwarf, which is a bit yellow-orangey here. Mountains, clouds, and another planet. I don't know, but okay. But there's another planet here. It might look like this. So this is a planet where there's a possibility of life. Okay. So we need stuff to have life. Of course, life hasn't been discovered outside Earth yet. But we're looking for it. So that would be the discovery, well, of ever, right? I mean, life outside the Earth. That will blow minds away.